Swayam Prabha. Digital India. Educated India.
Okay, I am going to begin with some practical problems and try to show how they introduce notions which are mathematical and somewhat abstract. So, it is a practical problems which guide you what you need to introduce. Then we generalize from there purely mathematically and then get some new consequences which in turn feeds into further technical things, and finally it will end up at, I will not describe it today, but it will end up explaining how the GPS works, global positioning system. I will not talk about it, but it is aiming towards that. So, I am going to start with the practical problem which everybody knows. You are all familiar with maps, right? Google map or whatever. So, typically maps will show various roads and markings on the buildings, etc., tell you where you are if you position yourself and plot the route, right? The maps are typical places which are marked, as well as there is a tiny scale at the bottom somewhere right side, which will tell you that this is the scale, and then you can roughly measure and say, okay, it will take about 20 kilometers or whatever, and get an estimate of that. So, problem I am posing is the following. So, map has these two ingredients. Places of interest are marked, and there is a method of estimating the distance between the two given points. That is the basic feature of any map. So, I am trying to now find out. So, map means places are marked and distances can be estimated. Now, what does marking of places mean? You can either say label it, okay, this is a restaurant or this is a building or something. But more importantly, at least some of the maps, if you see, if you hover the mouse, you will see there are coordinate labels. That is two numbers, like some numbers, or if you look at any sky map or astronomical charts, you will see some theta phi numbers there, right. So, marking points means you are assigning some, if you are looking at surfaces, typically two numbers. And then, so if you are given some marking here, this is maybe this is where you are, this is where you want to go. You are given some numbers here, say x1, y1. Here are some numbers x2, y2. I will come to it in a minute in more detail. So, these numbers are something that is visible on the map. Okay, and you are asked the question, well, if you were to go straight, how much is the distance between these two? Huh? Distance formula, very good. So, let us first see how do you assign these coordinates. How do you assign the coordinates? They choose an origin, okay. Then
we draw vectors from the origin to our position.
Then
we assign coordinates to these points.
What coordinates do you assign? What numbers do you assign?
Based on how many steps you move
Right, good. So let us do that. Since he said vectors, I just deliberately drew some arrows. Let us use the more conventional one. So, you make a grid, essentially take a graph paper, you make a grid, and in the grid there are lines which are marked, which could be number of steps you carry in one direction, number of steps you go in other direction, and so on. And you say this is the point at which I am getting, these are the values, number of steps along x axis, number of steps on y axis, and then I know the distance between them is nicely given by x square plus y square square root, right. Very good. Now, suppose I give you, so this is one way of putting, so this is the graph paper, so this is called say Cartesian grid, okay, orthogonal direction, two directions are orthogonal, you draw this graph. But suppose then I change it to something like this, and now my grid is made up of in the following way. There is some point, again I am marking same walk so many steps etc., but I walk not with this angle, but with the angle which is say some angle theta. Now ask the same question, what is the distance between this and this? My points are the same, except that in one case I use the grid which is like this familiar grid, other case I am using a grid which is different. What will I find it? How do I find the distance?
Will we add two vectors?
Yes, which vectors?
We have a horizontal component.
This one?
Yes.
This way? Okay. And?
And then you have your vertical component.
Yes. So you essentially go back to this, right? And again use the Pythagoras formula, right? Very good. But if I were to write in terms of, let's say here I denoted it by say x and y, here I denote by a and b. So the coordinates of the point here earlier were xy, now it is ab. In terms of ab I want to describe, what will I write? The formula will be something like a square plus b square plus 2ab cos theta. Okay, so this is d square, whereas here it will be d square is equal to x square plus y square, right? Very good. It's the same kind of thing that one has. Let me make it little more general now. I use a similar method, but now I take an axis, make an angle, some theta. Along this line again I go so many steps, and at this point I will put the coordinates to be number of steps I have gone along this, which is r, and this angle theta. Okay. So now my coordinates are r and theta given. What will the formula for distance be?
Distance will be r from the origin.
Along this, yes, very good. So this is okay. So this is just the coordinate system that I am setting up. I could have a different line. I will get a different theta because different points will have some r and some theta. But now I am going to ask a question about what is the distance between these 2 points. So this is r1 theta 1, r2 theta 2.
R2 minus R.
It is not as simple as that. Okay. So what you can do is, so let me draw the figure again. So here is my point. This is, let me take this together. This is point 1, this is point 2, and this is the distance that I want. So this is r theta. This is r plus delta r, theta plus delta theta. Okay. I want this distance. Yeah.
R plus delta R cos of theta plus delta theta minus R cos theta whole square plus R minus delta R square whole root.
Remember, I want only this distance.
That is
So this distance should only contain delta r and delta theta and maybe r. Okay, fine. I can't translate your equation so fast. How did you get it?
so we can draw perpendicular to the point and
So again, convert it to the Cartesian problem by components and use the same formula.
then we can
Yeah, no, I mean nothing wrong. That's correct. Other ways to say that I can also use the Cartesian formula by looking at this little piece here, find out what this distance is, what this distance is. So this is at the same radius, so this is delta r. This is supposed to be r times delta theta, but this is now a right angle triangle. Use Pythagoras again, you get the same answer. Okay, is that clear? Okay, so here the formula will be. So now we'll write notation which is little different. Delta r square plus r square delta theta square, right? Now, so notice one thing, there I have written x, y and a b, but I could easily write the points which are neighboring, so it becomes delta a, delta b and delta x and delta y. What is the commonality between these, among these 3 points? Sort of common feature. All of them have been derived by Pythagoras theorem essentially, right? In some way or other you either use vectors and then dot products, various things you do, but essentially that is what you use. One point to notice here is that all these distances are quadratic expressions in coordinate differences. right? Some coordinate difference, there is some coefficient sometimes. There is coefficient only, there are 3 terms here, a square, b square and ab, or delta a square, delta b square, delta a, delta b times something. So, it is a quadratic expression in general. With coefficient, in some case there are coefficients are trivial, just 1, 1. Other case the coefficient little bit different. Third case also they are little bit different. In particular, this coefficient has some, depends where I am calculating delta r, whether here or somewhere here, depends on the location, right. Very good. So, we keep this fact aside. So, delta s square. Now, since it is a general quadratic expression, I am just going to write it a slightly different way. I am just going to write it as g11 delta x1 square plus g22 delta x2 square plus g12 or say g21 delta x1 delta x2. That is a general quadratic expression. I have not specified what x1, x2, this could be x1, could be any one of these examples, right. And these coefficients here g11, g22, g12, g21, in this case it is just 1, 1 and g12 is 0. In this case it is 1, 1 and g12 is not 0, g12 is equal to g21 times that cos theta term. Here it will be first coefficient is 1, second coefficient is r square and there is no delta r delta theta term, right. Okay, so this is one fact we note and we proceed further now. So, I am going to erase this part, is that okay? All right. Let me now ask the question, fine, this is all seems to be working beautifully on a piece of paper or plane or whatever. Now, let me try to follow the method on a sphere. So, on this also I now want to follow the same method, choose some directions. So, I choose a direction here, go say eastward, this is earth, draw so many points and keep doing it. At this point make 90 degrees, go up, again certain number of points, say this way we go 5 steps, this you go 6 steps, and then again from here draw 90 degrees and continue and go 5 steps, come here, right. Now, instead of following this way, going this first and going that first, I now go the other way around, I go here first, same number of steps and go up, but I end up getting here. So, depending upon how I proceed, whether I go east first and then north or vice versa, I do not even get to the same point. So, I can't use this method for assigning labels. Method which works beautifully for these 3 cases does not work here. Now, if you want to make a map on just a city or something, which is fine, that first method is fine. If you want to make a map for all of earth, that method is not fine. So, we need to do something different, all right. So, what is it that one can do? Well, now I will make a little more jump and say, all right, if I do not have a surface like sphere, if I am going to generalize from my plane to sphere, why not just take an arbitrary shaped balloon, okay, just squeeze it whichever way. So, it has some random surface, random shape like this. It may have some holes also, does not matter. Now, I want to put coordinates on this. Of course, our earth is not like this, so we do not have to worry about holes there, but you can take this sphere anyway, it is not a perfect sphere, it is ellipsoidal and so on and so forth. But for if you are making generalization, why not go full steam, right. Here if I want to now assign coordinates, what will I do? I can choose some point, but that is of no use because the neighborhood of this point and neighborhood of this point is very different. So, there is nothing special, I mean it will depend upon which point I choose. That did not happen here in the previous examples, I could choose the point anywhere, it did not matter, I can't do that here. So, different method is adopted, we do therefore the same thing, we make a small grid, okay, but now make it with a rubber sheet, so that it is flexible. So, you take a rubber sheet, mark your graph paper on that, put numbers 1, 2, 3, 4, 5, whatever numbers you want, okay. Now, take that and stick it on top of it. Wherever it sticks to this surface, just below that there is some point, right. So, here is surface, I put it here, under this sheet there is some point, that point takes the same label as the labels marked on this. That's a simple enough procedure. I mean, it's easily doable. So by doing this, I get coordinate labels for points on the surface, right? Is that clear? All right, now there is only one problem, because I am going to ask next question. Fine, you have got these labels, but what about distance measurement? How do I estimate the distance? I don't know. Because I am giving a rubber sheet now, somebody stretches it more, somebody stretches less, somebody takes a different direction. Where sticking onto this doesn't stick the same way, may stick it in different way and so on. So everybody has their own choice of assigning labels. It's democracy, you can do that, all right, we accept that, but I still need to find out what is the distance between these 2 points. Remember, here it is plain sheet, once it's rubber sheet put on this, it gets stretched in different parts. So I can't use the Pythagoras theorem from here to write it here. So I have to do something else, but I don't know what to do. So what is the guidance now from here? We want to make some progress. What do we do? This is where we recall this expression. Okay. We say that whatever distance we are going to assign here, we don't know what it is, some distance for sure. If I really have the surface is steady enough, rigid enough, I have small meter sticks, I can go there and put it there or walk there, whatever, I can do so. So I will know the distance between them empirically, I can measure it, but I cannot do it always. So I need some formula, some practical method of doing it. I can get the coordinates, but I don't know how to write the rule to go from coordinate differences to the distances, that I don't know. But I know something from previous examples, that the expression relation between these is always quadratic. So I postulate that let there be some GIJs, so for distances, assume some distance, some coefficients, I will call them Gij. These Ij are 2 labels, each one taking value 1 and 2, just as here 1 1, 1 2, 2 2 and so on. So Gij has they take 2 values. So I need to give this. Now I know from previous examples, here they always comes in this together, which is easy to see otherwise. So this will be something which is will satisfy the property that this is same as Gij. If you interchange the 2 labels, it's the same thing. Not only that, here we saw the example, it depended on one of the coordinates in some complicated cosine function, so it's not simple power. In this case, it had well, r square I raised. So these coefficients may depend upon the labels, the coordinate labels that you put, right? So I could put them to be. Now general coordinates, I am going to write this simply as denote the x, some x, I don't know what they are. So this is going to be my formula, delta a square Gij of x, delta xi, delta xj. All right. I do not know what these are. I just taken some rubber sheets and stuck it there. I do not know what these are, but whatever it is, it will construct a quantity which is delta square, which is my definition of what the distance is. In the known simple cases, I know what this distance is really. I walk there or put meter sticks or whatever. Other cases, I don't know. Okay. But one thing which is certain, as you can see from these examples also, that if we make change in coordinates, instead of labeling them one set of labels, taking different set of labels, the distance between 2 given points always remains the same. Okay. That is this d square which is there. If I write this one or I change, rotate this coordinate axis, but between the same 2 points, the distance will always be the same, right? I mean, I am walking here from here to there. If I put a stick, you may take x axis, y axis like this or rotate like that. This distance doesn't change. This distance is whatever it is. So there is some quantity which remains the same even if I have changed the coordinate labels, right? Yeah.
At this stage itself, you assume the metric is symmetric because you know there is no torsion or something like that?
No, anyway, it's always symmetric, even in general case. It's the connection which is not symmetric in presence of torsion.
If there's torsion,
Yeah, but I am not getting there.
it's always symmetric.
Metric is symmetric. In the usual case, metric is always symmetric.
Do not generalize that to
No, no, no. One reason simple is simply it's quadratic expression. This is dxi, delta xi, delta xj. So it's symmetric in ij. So automatically only symmetric part will contribute. Yeah, yeah. So here there is no problem.
So there's no extra assumption of no torsion or anything.
No, 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 no. I will not even get there. I will be at much lower level. Okay. So this is symmetric simply because it has this form and this is under interchange of 1 and 2. It's the same. So therefore only symmetric combination will survive. So without loss of generality, I can take it to be symmetric. Okay. Yeah. So I was saying that. So we know that whatever we assign, you may assign one set of labeling, otherwise some other set of labeling. I must change my g's appropriately so that distance between two given points is always the same, which means this quantity is the one which is remains the same, or I call it is invariant under the change of coordinates. Okay. Yeah.
So where did the delta x1 square and delta x2 square go in that quarter form?
This one? Oh, sorry. Yeah, thank you. I am so used to it. There is summation involved in that. So summation means that this is actually compact expression. So this is same as g11 delta x1 delta x1 plus g22 this expression. This is same as is a compact version of this expression. So I am sorry, I am just too used to this, so I forgot to mention that. Yeah, this is summation convention. If the index is repeated, it is always assumed to be sum. Summed over how many values? Since we are looking at these two, x1 and x2, each ij takes two values, 1 and 2. So this is actually summation over this. Thank you. This is something so hard to remember that. Yeah. So this expression is same as this expression. And these deltas are the coordinate differences, whatever they are. But I do not know what they are, I do not know what these are. But I know that whatever they are, this quantity must give me the same answer always. Okay. So, and when I say this is distance, again in known examples, I know this distance is really distance. I take meter sticks and put them one after the other, I will calculate the distance. That is the physical quantity. That does not change upon how I label my coordinates, how do I stretch the labels and so on and so forth. It is independent of that. What changes is that these guys will change, these fellows will change. They must change. Because if this change and this does not change, this cannot be consistent. So this has to change when this changes in just such a fashion that this remains the same. Okay. So moral of the story is that this delta s square is the physical distance while the coordinates differences and these coefficients are called metric coefficients, the GIJs. Okay. They themselves, by themselves, they do not have any meaning. They have meaning only in conjunction with this formula. Okay. So, for example, if I go back to this example now, replace x and y by delta x and delta y, then it says that when I do such a thing, if I put 2 points where delta y is 0, then the distance delta x is same as the distance that I measure. The distance that I measure is the real distance, right? So this says that delta x is precisely obtained by taking difference between two distances along x axis. That is what the first formula says. Second formula will not say that. If I say that delta b is equal to 0, then of course it is still true. What about delta a is equal to 0? Is also true. So along each of these directions it will be real distance. But in combination, that's what you need the extra cos theta term. Okay. So meaning of interpretation of what the coordinates are can be deduced if I know what the GIJs are and if I know what delta s is. Clear? I am gotten from the ordinary map and doing distances to a little more abstract level of saying that if I want to generalize the notion of maps to something more complicated surface, like a sphere for example, then I need to generalize and not get stuck to the idea that I must always walk across and measure the foot. I just take any grid and put it there. but then I must remember, if I make this arbitrary freedom, I must also allow me the freedom to change the GIJs, and they must be chosen in such a fashion that this remains the same. Yeah.
Sir, how do we know that the distance for the expression for distance is always quadratic no matter the?
That is from the examples. In 3 dimensional also quadratic. I will just come to 3 dimensions in a second. Yeah, yeah. I will come to that. Yeah, yeah.
What are the coordinate differences in the metric coefficients?
Sorry. Yeah. While the coordinate differences, and the metric coefficients do not have meaning by themselves, can you read it? By themselves, but only in this combination this acquires a meaning and gives the distance between the 2 points. Okay, so that's the essential point I want to get. I will generalize in a second. So is this lesson clear? We are faced with the problem. I am familiar with some set of maps, what the distances are. I am now faced with the problem of generalizing it to Earth, let us say. Then I already need to make these changes. But now once I make the changes, then let me go one step further, go to arbitrary fellows. And now I see that I need to generalize in such a fashion that I must get this object. Okay. In general, I do not know what GIJs are and what delta x's are. I have to specify that. Only after it is specified, I know what the distances are, vice versa. Okay. So now let us go to one step further. Is this part clear? Because I am going to go generalization of that. So coming to your question, this was in 2 dimensions. Well, if I were to do it in 1 dimension, what will I get? I will just get a line and delta x square, that is all. If I have 3 dimensions, where will I need 3 dimensions? Not going in a city but in a car or something. So why would I need 3 dimensional maps? Yes. So for example, I am going hiking, I go to some peak, some height, and I have to go to some different peak, and I know the road is all winding and so on and so forth. But if I were to take a plane or as the crow flies, the distance will be different. That is the distance I want to know. So therefore, now I need feel the need that I need to go to 3 dimensions to address this issue. So what do we do? Well, we simply generalize the formula, same expressions, but I, j variables take 3 values, 1, 2, 3. That is all. It is still a quadratic expression. Why? Because if I take these 3 dimensions, I suppress 1 dimension, take one of the delta x equal to 0, remaining points has the same formula as before. So if I want that property to be true, I must generalize in such a fashion that is again a quadratic expression. Okay. So now I have the general expression delta s square gij delta xi delta xj ij equal 1, 2, 3. Okay. That is a generalization, just writing one more symbol, right. Is it clear? So it is a rather straightforward generalization, but now I am going to ask next level of question. Fine, this is all okay if you are talking about cities and maybe some hiking and so on, but if I am really talking about distances which are very far, so there is no way I may have cartographers will go painfully over a period of year maybe and put labels, etc., etc. But I need to find out these very long distances. What do I do? Well, one method is to say if a very far distance I clap, then the sound goes there, presumably it comes back, my friend will clap at the same time, I will find the time difference, say I know the speed of sound, I know the time difference, I know the distance. So that is one way to access the distance estimate by knowing, using something like sound which we are familiar with, and knowing its speed and finding out that time difference between the sound going that place and coming back. Fine. So that is one way we can access distances which are larger than what you can just walk around. There are a few problems there. One problem is that speed of sound is something which is not fixed. It will depend upon air pressure, it will depend upon temperature. Worse, if there is no air, there is no sound. So this method cannot work if I want to go to bigger distances like satellites. Yeah.
So could we use lasers instead because they receive sounds?
Coming to that, yes. Okay. So, sound is something nice is the first thing that occurred, and people did use that. I mean, you still shout at somebody, no? So you know the distances sound can be used, but it is not useful for this problem, because it's the distance now. So what I am doing essentially, the distance is being converted, this distance is converted in terms of time. I am introducing one more variable which did not exist here. This is only x, y, z. Now I am introducing one more variable to put it here. Say this distance is the physical distance as crow flies, okay? And there, if I know the time difference, I will just multiply by speed of sound, and then say this is the distance. Speed times the time is the distance, right? So I can convert this side into this method. But now, as I pointed out, that sound is something which will not be available if there is no air, or if the air goes down, pressure goes down. So that is not a very useful method. It's viable for some distances, but not all. But there is something else which is given by nature to us, namely light. Fine. So, and also speed of sound is not all that fast, so it does not really also diminishes and so on and so forth. More problems are there. So while it is a possible method, it is not very useful method. But now you can use light. Okay. You pointed out laser. I may use laser or whatever. Laser is one method, since everybody knows, you can just take it out and shine there. Essentially, it's the light that I can use and flash a light from here. It goes somewhere, maybe it comes back. You put a mirror there, or your friend flashes it back. Know the time difference, you convert it. Advantage of light is it does not need to have air in it. It propagates even without air. That is one great advantage. Okay. Secondly, it is very high speed. So you can cover longer distances. Third and most important thing is a property of nature. Speed is always constant. Speed in vacuum or almost no air. Okay. This speed is always constant, and it does not depend upon whether the flashing laser is moving or not moving. That is a property of nature which has been discovered over a period with a lot of experimentation and so on. That is something that we accept. Okay. But if that is the case, what advantage do we have? Because now we are really in good shape, because this conversion from distance to time to distance is always fixed. The same constant c, which is the speed of light, is denoted c, which is about 300,000 kilometers per second, right? Unlike speed of sound, which will be only about 1100 or so kilometers per 330 meters per second. Okay. So this is greater speed. It is independent of this. So this methodology will always work, because the speed of light is always constant. So what do? I replace this guy by c square delta t square. Okay. This is sort of very simple thing to do, going from here to there. All right. So I erase this now. So we use this fact of nature which is available to us and write this. But now the fact that speed of light remains the same will also impact in saying, remember this part I said that I can change my coordinates, because my labeling can be changed. I can stick the labels in different fashion, but my metric must change in such a fashion that this remains the same. But if this remains the same, this will also remain the same, provided delta t remains the same, right? But that is not guaranteed. At least we do not know for sure, and we have to examine whether that is true or not. So this will remain the same if these guys are changed. This I do not know. I am just putting it, simply saying that delta t is this property. Now what I am going to do is make one more jump, so to say, and say that I will generalize the formula to say delta s square to be, I will include this guy, put it on this side, and then write it as g mu nu delta x mu summation mu nu equal 0, 1, 2 and 3. These are my x, y, z coordinates. This is my new fellow that I introduced t, and sort of more or less straightforwardly generalize that expression to this expression. Okay. So far it does not look terribly revolutionary, it's rather simple to write that, but there are of course many things hidden in it. Here delta x's I know I can change. What do I mean by changing delta t? X's were arbitrary coordinates because they just depended upon how I took the thing. What about this t? Who is t? How is t decided? I say my watch, your watch, it goes. But by writing it this way, I am putting delta t on the same footing as delta x. If delta x can be changed, so can delta t. They both must change in such a fashion, and this guy must change in such a fashion that this remains the same. Is that point clear? Sort of following the same logic that I use for the so-called real distances or special, yeah.
So how did we get 0 also?
Oh, it's just a labeling. The t is what I am calling 0. I could call it 4, but convention is to call it 0. Yeah. So that's why I say this corresponds to x, y, z, and this corresponds to t. But by saying it, I am already demoted t from something which is fixed to something which may change. Okay, recognize that, because just as x, y, z can be changed to r theta phi or whatever else, so can this. How exactly it changes, etc., etc., there are different reasons. I will come to that, little bit of that in a minute. Okay, but by writing this formula already implied that such thing is possible. I am admitting the possibility. Ah, yeah, yes, you are right. That I will write when I write it here. Oh, here. Okay, I can write it CT. Sure. Yeah, you are right. I was going to write when I write next, but that's okay. Correct. You understand, because dimensionally it is these are obtained by measuring. Although I have now decoupled from that, but initially they came from distances, length dimension. C times t is the length dimension. Yeah. No, this delta t again is the time difference, right? I am saying that when this part is fine. This is just a statement that this physical distance L, so many kilometers is c times delta t time required for to travel back and forth. But now I am going one step further. I am saying that I am putting this formula by bringing it here. But this is now saying, if I interpret this formula the same as interpreted here, then what does it mean? The space part of this. So I can write it as, say, g00 delta t square. Let me take it g0I delta t delta xi plus gij delta xi delta xj summation ij summation I equal 1 to 3. This is 0 0, right? This is the same expression as that, right? So this part we understand how we change, right? This part we don't know, but by putting it on the same footing, I'm allowing for the possibility. Maybe this is just as we assign the coordinate label x, y, z by taking graph paper. I'm now going to assign events, some entity called events, a timestamp. So things which happen now, not only they happen at this location, but at this time. So I'm assigning a time coordinate. Okay. So I'm not talking about only simple distances anymore. I'm going a little beyond that. So here I would have called them points. Here I will call them events. So events just means that this is something which happens at the space label x, y, z and a timestamp. Okay. So this time stamping procedure, although we are not discussed in detail as to how the time stamping is done, that's a separate part. I mean, normally one will do it that way when you introduce special relativity. I will bypass that step, but I will get the same results in a slightly different fashion. But we have to assume that this can be different. We will explore the consequences of what does this mean in a minute. Yeah, is this part clear? So just writing this way, I am allowing for the possibility that there is a time stamping to be done. This is again time stamping of two events with the coordinate difference delta t is delta t. This delta t is no longer the distance time of travel from going from point A to B and come back. So I change the interpretation of what delta t is. Okay, but I sort of followed the same logic to come here. Okay. Now we had the simplest example of space part was our Cartesian system, right? So there we know that, oh sorry, it went off, the delta x square plus delta y square plus delta z square. So the metric coefficient Gij's were simply 1 1 1, right? So corresponding statement here would be saying that delta s square is equal to g00 delta, sorry, okay, g00 delta t square plus delta x square plus delta y square plus delta z square. or delta x1 square plus delta x2 square plus delta x3 square, same thing. Is that okay? x1, x2, x3 same as x, y, z. Okay. Now notice that when I put this coordinate difference, so now two events. What are the two events? I flash light here, it goes to the wall, comes back, that's my second event. So time stamping of these two events, one is t equal to 0, second is delta t. Okay. So I am now using the fact that this delta t is time stamping of two events. What are the two events? One is flashing light, second point is light is received. These two events have time stamping, x, y, z coordinates are the same because I am at the same point, but it takes some time to go and come. So that is delta t. But this I know corresponding delta s is 0, but the distance it has traveled is exactly that. That is what we used here. Okay. Now this can only happen if I take this guy to be equal to minus 1. So that this equal to 0 is this expression, which is same as this expression. Okay. This is not the most general expression, this is the simplest expression one can write. Just as the simplest expression was Cartesian coordinates, distance square was delta x square plus delta y square plus delta z square. I am writing now the distance between two events is minus delta t square plus delta x square plus delta y square plus delta z square. This is part we know, this is something I added, and I put a minus sign for the simple reason that otherwise I won't get delta s equal to 0, right, because that came from here. Once I describe what the two events are, flashing of light and receiving the light, I know delta t, it has gone that distance, which is delta x square plus delta y square. That must satisfy this relation because speed of light is given to me, it's fixed. Okay. So this has to be 0, but this cannot be 0 unless there is a minus sign. So this is the thing that I use. Oh, sorry, c square. Thank you. I keep forgetting this. We're used to putting unit c equal to 1, so we just we forget about c, but you're right. Is this part clear? Because from here I am going to go next step. If you have any questions, please ask.
You have gone from space to space, right?
Yes, yes, but without using those words, yes. They motivated it from the practical problem of wanting to know the distance estimate, and then if the distance is large, you have to use light. If so, then now you generalize it to there. So that's how I followed the logic. Yeah, go ahead.
So please go through one more time why we have minus square root.
Yeah, I put some G00, right, which I didn't know. Now I am saying that consider two events, just as there in the x, y, z, in the Cartesian points I took x, y points, right, general points were delta x square plus delta y square. But I could take 2 points which are along this axis, then it's just delta x square, or here it will be delta y square. So I can always choose two different events and ask the question what is the distance between them. For the space part it is clear. Now I am asking the question, let me choose my delta x, delta y, delta z in such a fashion. Let us say delta y is 0, delta z is 0. So this is my x, y, z coordinates. T equal to 0 is when I flash the light. That wall there reflects it. This distance is my delta x. The light goes and comes back, and I know delta t. So the two events here which are gone from there, distance delta x is 2 times delta x, of course, and I know that 2 times delta x, c delta square is equal to 0, because that's how I found out the distance. C square delta d square is equal to delta x square, right? So that being the case, I must get the same answer here. So this should be 0, but this cannot be 0 if this is also positive. So therefore sign has to be negative. Yeah.
Now that we included time into the expression for delta s, how do we know whether delta s still represents physical distance?
Coming to that, yes, good question, good question. Yeah, I will come to that, yeah. Yeah.
Delta s is not the distance between events. Time is
This guy is the generalized notion of distance. Let me use the word interval just to distinguish from the distance. It is like distance but not the distance, because distance by distance means space distance, spatial distance. This is something interval between two. So, right. So if I am only talking about points in this 3-dimensional space, this point and this point, I have delta x square, delta y, z, etc. But I am talking about something happening here at time t, something happening here at time t2, then I am talking about two events, not 2 points. So, yeah, event interval is the analog of this delta s square. So this has now gone from mere distance to event interval. So I made that generalization. Yeah. What was your question again? Sorry, sorry, I forgot because.
Yes, sir. So now that we have included time
Yeah.
into the equation for
why
delta
is
S,
this
how do we
not-
know it still represents physical distance?
Right. So this is not the same distance as when this will be distance again, provided delta t is 0. Okay. So if I have two events which are simultaneous, t1, t2 are same, then this delta square will recur to that. Remember, this is not, these are variables, there are different sets of points I can choose. For special cases, I will get certain value. So this generalized notion of interval, let me now use the word interval, will match with the distance provided delta t is 0, will be equal to 0 if these two deltas correspond to light flashing and coming back. But if it is not the case, for instance, I may have delta x equal to 0, I am sitting here and just watching time, tuck, 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 tuck. So all the events are the same, x1, x2, x3, delta x is 0, delta y is 0, delta z is 0, but I still get some time interval, then these terms are 0, I will just get this, so I get a negative answer. Unlike the previous distance that we talked about, which was always positive, because you can walk there, this distance can be positive, negative or 0. So this interval can be positive, negative or 0. Because of the fact that there is a minus sign. Yeah. They will be complex only if you put, these guys are complex. Yeah.
Or interval itself is defined as
Exactly. Good. So I don't take square root to get a minus sign I there. Yeah. So the point here is that, so I generalize the notion of these distances to this one, to this interval now. I will call it, I may still call it distance, but please understand when I write this, either mu nu expressions or this expression, it really corresponds to interval. The distinguishing property of this is positive, negative or 0. Unlike the previous case where distance between 2 points was always positive or 0 of course, this can be positive, negative or 0. When is it positive? This is called space-like distance. So this interval is space-like, for obvious reason it looks like space, it's positive. If it is equal to 0, it's called light-like. It likes light because you are talking about the time of travel coming back, so just the light travel time. And if it is less than 0, it's called time-like. Why is it time-like? Because this is a special case. If it is, yeah, no, it is time-like because if it is negative, I can always choose events such that all of these are 0. So the only thing that changes here is the time. So it's time-like. If I take, if this is positive, then I can set delta t to be 0 because this is still positive. And the only thing that changes here is the space. 2 points, the spatial coordinates change. So it's space-like, this time-like. And if it is exactly 0, then I cannot put either of these separately 0. One of them must be non-zero, one of these must be non-zero. So it's light-like. Okay. So we have gotten somewhere. Is this part clear now? Because now I am going to ask more questions. Is this clear? Yeah.
There might be cases that the magnitude of delta c square delta t square is greater than the sum of the space coordinates. Then also delta square will be less than 0.
Yeah.
That is also be on the space.
Sure.
But there's change in the space coordinates.
No, I agree. I am not saying that this can happen only when this is 0 or not. I am saying if it happens to be, let us say, positive, then it is possible to find two events where this is 0 and this is not there. If it is negative, then I can choose this to be 0. That is what I mean. Yeah. So I am not saying that every time it has to be that. No. Okay. If I want to draw a picture, just in case, I don't know if it will help, but let me draw it. For just one dimensional thing, because that is the picture I can draw, 2 dimensions is a little difficult to draw. Then I have the following picture. This is my t axis, this is my x axis. Okay. since I do not have here GIJ's off diagonal pieces, so it is, I can draw this as a vertical line 90 degrees, although 90 degrees here has no particular meaning. Now you can see that this 45-degree line this 45-degree line will correspond to delta, sorry, this light like interval. So any 2 points on this will satisfy the relation c square delta t square is equal to delta x square. Is delta x square, this c square delta t square is 45 degrees, so they are equal in magnitude and the sign is opposite, so it will be equal to 0. So 2 points along this line will be light like interval. Okay. What about 2 points which are something like this? Then I am getting something here, but these guys are smaller. So this is positive, so this is space like, and likewise now it's a simple guess, this should be time like, right? That's the only part which is left, so that must be time like. So if we had not the minus sign, then we just x and y axis, then everybody is positive, there is no distinction like this. Okay, is this part clear? So yeah.
So since delta square is in this case is one dimension, it will be delta x.
Just one of the coordinates, delta x or delta t is there and delta x is there. Yeah.
So delta square will be delta x square minus c square delta t square.
Correct.
So c square delta c
That is there.
delta t square is always positive. C delta t is always positive.
Yeah, because delta t is real, so delta real number square is positive.
So
Yes.
x can be negative. Delta x can be negative.
Oh, delta t can be positive or negative. That's fine. I mean, see, if I look the event this minus this, I am not talking about going forward or going backward. That's not what I am talking about. I am only talking about time stamping. So when we say that if it is larger, this has happened afterwards, other will say it has happened before. Delta t, which is just the coordinate difference, that can be positive or negative. But what enters is the quadratic expression. No, so in the delta s square it doesn't matter. Yeah, that's correct.
So for the graph, it will extend to all quadrants.
Yes, yes. Oh, yeah, sure. Yeah, I mean, can also have this. Various things. Yes, sure, absolutely.
You mentioned the light cone to try.
Yes, it's already there. I was about to think of that. This portion, this region, this is called a light cone. And this region outside, this is also. So this forms a cone. If I were to go to two space dimension, one time dimension, then let me draw the figure. So I have drawn a light cone from origin. So this is my t axis. This is x axis. This is y axis. So now imagine this is x axis, y axis, and what we will call z axis I am calling t axis, because we are in two dimensions, two space dimensions. Okay, I am not sure this picture is good enough, but I will try to. This is x axis, that is y axis, and z axis where I am standing is actually time axis. So I draw a circle around it, this one, which means x y values. So in the x y plane it is a circle. So I draw a circle here. At different times I see my same circle, but now I take the 45-degree lines going from there, passing through the origin, that forms this cone. That's why it's called a cone, shape of a cone. Regions inside all of this will be time-like. Regions on this will be light-like, and regions which are outside are space-like. Simplest is the one-dimensional picture, because that's where it is easier. Here it can be a little more dicey, so let me not. It gives the impression of cone, but one will have to worry about a little more. So, okay, I won't need to use this picture, but since you mentioned, it's called light cone, and this first picture I do is called Minkowski space-time diagram. That is just in case you want to Google search. Minkowski space-time diagram is the name for that. But I am not going to go into that now. I am going to go to a different problem. Okay. So, let me erase this. Remember, I mentioned that the coordinates by themselves do not have a meaning, metric coefficient by themselves do not have meaning, it is only the interval which has physical meaning, but that is the one which either says is real distance or real time interval. Time interval on what clock? I have not specified that. So, now I want to ask the question that if we have this expression, that one on the top, okay, what does it tell me? So, I claim it will tell me that two different clocks which are in relative motion will tick differently. Okay, I claim, and I will try to prove that using that formula alone. Okay. So, all I know is that the space time interval, I mean time in that our notion of interval is given by that, and in fact I do not need all three of them, but let me keep it does not matter. Okay. I am going to now look at two clocks. I do not know what delta t means, I do not know what t means, I do not know what x means, y means, they are just coordinates. Their coefficients are the metric coefficients. All I know physically is the delta s square, and if delta s square is positive, it is space like. So, that will really correspond to distance. If I took meter sticks, I will get that value. If it is negative, it will be time like, it will correspond to the statement that it is time interval on a particular watch, physical watch. It is not some label which is assigned somewhere. Okay. And if it is something in between, that will not look at, will not get there. All right. So, this is the part I want to look at. So, now I am going to, since time intervals are, you will say delta t square is real. So, I will define it as follows: delta s square equal to c square I equal 1 to 3, I am just saving writing. Okay. This is x1 square plus x2 square plus x3 square, 3 terms there. Okay. Now, I am going to look at trajectory. So, this is my map, right. The previous one was a map in the sense x, y, z coordinates were given and the distance was given by that rule. Now, this is my map which I will call Minkowski space time, or let us just call it a map, but which involves the time the time stamping and distance labels. So, that is what map is. Now, on this map I can ask a question. I am sitting in a car, I have a watch in my car and I am driving around, but I am driving simplicity with uniform speed below the speed limit. Okay, I am doing that. My watch is showing some things. So, I ask the question, whenever the watch shows something, I flash light, 1 second later I flash another light. So, these are my two events. Since I am moving on the road, my first event is here, second event is flashed at that point, right. So, I say that my motion of a clock is given by delta xi is equal to vi times delta t. So, x component of the velocity, y component of velocity, z component of velocity multiplied by time is the corresponding delta x, delta y, delta z, right. If I am moving with uniform velocity in time delta t, I cover a distance delta x in the x direction, v x times delta t, v y times delta y and v z times delta z. So, this is what I get. Okay. So, my delta t is defined by flashes of lights which are given by my second. First second, second, third second and like that. In that I cover a distance delta xi which is given by v times that. V is my normal speed Gaussian speedometer. For this case, if I want to find out what is delta s square, what will I get? So, for this delta s square equal to minus delta t square, sorry again c square, this is okay. Sorry? Yeah. Let me write, yes. C square delta t square plus delta t square summation I vi square, right. So, this is same as minus delta t square 1 minus v square over c square. V square is the velocity vector square, so the speed square, right? Is this fine? Since now I cannot go faster than speed of light, okay? So just as the intervals were divided into positive, negative and 0, it turns out that the speeds can either be always greater than speed of light, or exactly equal to speed of light, or always less than speed of light. There are 3 classifications you get. That part of special relativity I will not discuss. Okay. So since we are talking about, I am going in a car, I am sitting here, so this v is always less than speed of light. So v is less than c, this is always positive, this is positive, therefore delta s square is negative, which is fine because the interval is defined by the clocks. So I will call this as minus c square delta tau square. Delta tau square is positive. So I define delta tau by this relation. This interval is c square times delta tau square, the minus sign. Okay. Is it fine? This is just algebraic change. I have calculated this interval for a clock which is moving. I find out what the interval is. I just call that interval as minus c square delta tau square. So this c square cancelled and delta tau square is equal to this one. So this tells me that delta tau square delta t square 1 minus v square over c square. Right? This is just convenience for getting rid of the sign. All right? Yeah. Yeah, I am just coming. Yeah, just 1 second. Since this is related to this, this is something interval. That's a physical entity. That's a real quantity. Okay. So now let's ask the question: if the clock were not, if the watch were not moving on my map, so that the coordinates were not changing, that is v equal to 0. V is called a coordinate velocity, because what is changing with the clock is the coordinates are changing, right? Coordinate differences are generated by the time intervals, right? So this is coordinate velocity. Okay. If coordinate velocity is 0, then this delta t same as delta tau. Delta tau is physical interval, and now that I have adjusted sign is the time interval. So this delta t that I am talking about corresponds to the time interval as measured by a watch which is not moving with respect to the map that I have. Is this part clear? So let me write it. I will maybe need another 10 minutes or so. Is that okay? So we see that delta t is the time interval measured on by a clock or watch which is at rest with respect to the map. By map I mean whatever grid I have laid down, okay, by real map that I have. So I obtained an interpretation if v is equal to 0 from the same formula. So that means the watch is not moving. T, x, y, z have been assigned whichever way. I am finding out what does delta t mean. Since this equal to 0 means this is equal to that, and delta tau is a time interval. So this is time interval measured by whom? By the watch which is at rest. Okay. So this is the meaning of what delta t is. Using the expression for the metric and coordinates, obtained the interpretation of what delta t is. Is that clear? Okay. Now what happens if the speed is v? Now take a second clock which is actually moving. Then this one, delta tau square will be this expression, right? This delta tau is not same as the previous delta tau. Previous delta tau was something where a watch is sitting, and for each of its tick, 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 it is flashing and finding out what the delta t is. That is delta tau. Now I am defining a different two events, namely by watch which is moving, which is flashing light with its clock. Tuck, 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 it is doing. Yeah.
When you said the flashes of light is shown after each tick, the tick is according to the watch inside the car or outside the car?
It is the clock in the car. Yeah. If V is equal to 0, then it's the same as watch for the person standing outside.
So delta t is the time interval of the person who is sitting inside the car.
In general, sitting inside the car, yes.
And tau is of that person sitting.
Tau is the interval defined by the two events which are to be specified. Unless I specify the two events, delta tau has no meaning. So I must specify what the two events are. This is the most, I mean, all the relativity paradoxes that you will come across are related to not identifying what are the two events that you are talking about. Once you know the two events, the formula will tell you, you will be safe. Yeah. Yeah.
Sir, if you take, so delta t, which is on the left hand side, is the delta t time interval measured by a clock which is at rest with respect to the map.
Yes.
So, sir, if we keep the map,
No,
which is
wait. This delta tau is just the time interval because this is positive, time like interval. So whatever is the between two events which are defined, whichever you define, this delta tau is the two events whose interval is time like will define the delta tau. I am now saying what is delta t. Okay, delta t for what? I am defining the two events by a watch which is flashing light as per its tick tock. Those
Sir,
are two events, consecutive events. For that, the corresponding interval is always delta tau.
sir, so which delta t is with respect to with
The clock
stationary
sitting
with
at the
respect-
stationary. With respect to map, it is not moving.
Sir, which one?
Delta t. See, delta t is the time interval, okay, defined by ticks of a clock, which is not moving with respect to the map.
Sir, there are two
Because
delta
then the v is equal to 0, right? Clock is not moving, so v is equal to 0. Then it is equal to that. This time like interval, so this time interval is same as that. In other words, delta t is the invariant interval, therefore it's physical. Okay. Earlier delta t was just some labels. Now I am saying that who is delta t? Delta t is precisely the intervals which are physical intervals defined by two ticks of a clock which is at rest with respect to the map.
Sir, so if v changes,
Yes.
if v is something which is not 0,
Yes.
then which delta t would change? The left
Delta
hand
t
side or
remains
right?
the same because my map coordinates are fixed. My two events are changing. So in my diagram here, okay, this is my clock which is moving, okay, it's some speed v. My t axis delta t is this one, whatever delta t's are there. Who is the delta t? If there is a clock is not moving, this line is going to be like that. That clock ticks are same as these ticks, whereas the clock ticks which will come here will be like that. So I have to find out which two events I am talking about, and that corresponding interval will give me this. Is that clear? Yeah. Yeah. So in the first case, I consider events defined by two consecutive ticks of a watch. Okay. In general, events are defined by this. There are two cases here. A, watch at rest, always with respect to the map. So relative what I am talking reference is always the map, and B, moving on the map, moving with relative uniform velocity. I am considering two separate cases. Okay. So this will define for me a delta tau 1, let us say, this will define me delta tau 2. The intervals will be different because two events are different, right? But because the events are defined by the ticks of a clock, and since the events are different, their intervals are different, the second as defined by a moving clock is different from second as defined by the clock at rest. I will repeat my sentence. I have defined two events. Two events are defined in two different ways. But events are always defined by saying there is some watch which is giving tick, tick, tick. So two consecutive ticks defined wherever the location is on the map, delta x1, etc., and delta t. Now, if the clocks are in two different clocks are in two different motions, and they define different events, different pair of events have different intervals. Okay, because the intervals are defined, they are different, and they are defined by the ticks of two clocks, which means that two clocks don't tick at the same rate. Okay. Explicit expression I will write in a minute, but you get the point. Notice one thing, given a pair of events I have an interval. I am looking at only those pairs of events which are whose interval is time lag. Okay. So, we will first of all restrict to that and forget about delta is positive, 0, etc. Okay. Now, give me a pair of events, I will give a delta tau. Now, I take this pair of events, I get one number. I take this pair of events, I get different number. This pair is defined by a clock which is moving. This pair is defined by a clock which is not moving. Intervals are different, but intervals define me what are the seconds, because the ticks are telling me what is 1 unit of second, right. So, the two clocks are having two different intervals, and therefore, this interval being different, which says that the two clocks are ticking at different rates. Is that clear? If not, ask. It will take little time, but let me write the expressions in a minute. But basically, you see there are two events, one pair of events with one clock, other pair of another clock. If two events are pair of events are different, their intervals are different, but intervals correspond to the ticks of clock, which are seconds as defined by clock 1 or clock 2. Since they are different, the clocks tick at different rates. There is no flow of time which is doing something uniform, all that is ground. I am not talking about that at all. I am talking only about as something which is measured and defined, namely clock ticks of a clock which tick 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 do. The clocks need not be a watch, it could be my heartbeat, it could be something else. I will come to that in a second. Okay? Just some periodic event which gives uniform ticks. If the ticks are in relative motion, the rates are different. That is just a consequence of this statement. Just given this expression, we can derive what it means, knowing that these by themselves have no physical meaning, only this one has physical meaning. Is that clear? When you study special relativity, you will derive the same result with a slightly different argumentation. I am basing it entirely coming from maps, because we know 3-dimensional ordinary space maps. I simply generalized, gotten to this result will be consistent with that, it has to be. Okay? But I am arguing from the point of view, if you give me a map and this rule, then I will derive everything else. Namely, the time dilation. What is the formula for time dilation? Now, I already told you that two events are intervals are different. What is the relation between two intervals? Obvious question, right? Well, we have one which is v equal to 0, one with v not equal to 0. So, this is delta tau as defined by a clock which is moving. So, let me call this. So, this expression delta tau v and remember this delta t is nothing but delta tau as defined by clock at rest. So, I am just call it delta tau at 0 and of course, square and 1 minus v square by c square. Okay. Remember this notation is little different from what we will come across. Usually the interval will be this 0 and v will be reversed. But since I am following a certain logic, I am following the corresponding result. This is a reminder that this is the clock which is moving with velocity v, speed v. This is the clock which is not moving with respect to the given map. Okay. Its time interval ticks are defined by delta tau 0, these are defined by delta tau v. The relation between them is given just by that, which is same thing as saying that delta tau v, delta tau 0, square root of 1 minus v square by c square. Okay. But this quantity is less than 1, so this is less than 1. Okay. So, for example, if this shows 10 seconds, this will show 15 seconds, just to give some numbers. Okay. So, this fellow will conclude that this clock is moving, it is slowing down. Okay. Go over this formula yourself. Algebra is very simple, algebra is 3 lines, but interpretation of what is meant by delta s or delta tau, what is meant by delta t is crucial ingredient here, and what are the two pair of events you define. Once you get this thing clear, rest is clear. Yeah, yeah, go ahead. Yeah.
Sir, can we define the map itself as being moving? The map itself is moving it with respect to that decalculated velocity.
With respect to which map? It's moving with respect to which map?
We have said which
Yes.
is moving with respect to a stationary map, let's say.
So you have two maps.
Yes, two maps. One map is moving,
Yeah.
and then on that map.
By map, what do you mean? X, Y, Z, T.
Yes.
Okay.
So
So
that
X, Y, Z, T moving with respect to Z means what? I know what X, Y, Z moves with respect to another X, Y, Z. This plane moves with, what is X, Y, Z, T moving with respect to that? I know what X, Y, one map, X, Y map moving with respect to X prime, Y prime. A plane sheet goes like this. But what does it mean to say a map which is X, Y, T moves with respect to X, Y, X prime, Y prime, T prime? What does it mean to say two time move with respect to what?
So let us say that you are defining a map which has its origin around something which is moving.
Okay, so fine. Now, this expression which is there, it is possible to have another expression. This is just to answer his question. You can have a different set of coordinates labeling x prime, y prime, z prime, t prime, such that the corresponding intervals are given by this, but they still give me the same delta square. This is a coordinate transformation. If you call this as a two different maps moving, yes, you can do that. And then the fact that this has this particular form will say that these transformations have to be what are called Lorentz transformations. That is because I have chosen this specific form. This is like saying that if I have two-dimensional Cartesian coordinates, x and y, x square plus y square is something given. This grid, I have got this grid, I have rotated, I have x prime, y prime. Okay. For same points, I have two different sets of coordinates. One is x, y, other is x prime, y prime. The distance is invariant because I have rotated. There is a formula which will say why it is invariant, when it is invariant, and so on. So, if you want to say this as two maps moving, then yes, you can have a different map which has the same physical intervals. Remember that, just as the delta here was the same. Okay. Then the maps, the coordinate transformation have to be related. Yeah, you had a question. Yeah, 1 minute. Yeah.
Okay, so if V is equal to C, then our time interval is going to be equal to 0. What does that even mean?
Good question. I said that if there is a watch which is at rest, it cannot go to speed c. All speeds are divided into three classes. Either you are born with speed of light and stay with that, you cannot change it. There is no frame in which you can move where the speed will change. That's the statement, speed of light is constant. If you have speed less than speed of light, you can never reach speed of light. If you happen to be born with speed larger than speed of light, you can never come down to rest frame. This will follow from specific properties that you will get from Lorentz transformations. I am not going into that mathematics, but that is a fact. So, you will not cross over, you cannot get this to this. The limiting case, you can get it very close to 0.9999 you can get, but not equal to 1. Yeah, yeah, sorry, he had one question, then come to you. Yeah.
So we'll assume it to be the limiting case. Then if some objects travel with the limiting case of the velocity, he will feel a near constant as time is not changing.
Yes, the clock will be very slow, yes. I will give an example in a second, just give me another 5 minutes and I will wrap up my talk also and say why it is real, and that is where I want to get to. Yeah, you had some question on this, then I will give me 5 more minutes and I will explain that. Yeah.
Yes, sir. So let us say we have one map, map 1, which is stationary, with as stationary as it
by
wants to
itself,
be.
there is no stationary
Yes.
map is
As
map.
by itself. And then let's say I have map 2,
Yeah.
and map 2 is linked, like the origin of map 2 is defined using a photon which is moving at the speed of light.
Doesn't matter, yeah.
Yes, sir. So now let's have an object which is stationary in map 1. In map 2, it will be moving at the speed of minus c. So if you substitute in that equation, that stationary object
No,
is
because
easy
the law of velocity of addition is not simply v1 minus v2. In special relativity, if I have one frame with respect to something moving at speed u, I am moving with respect to that with speed v, then that speed of that object related to that is not v1 minus v2. The law is more complicated to ensure precisely the question. Otherwise, I have speed of light, I go at speed of light. Does that become speed 2 times c of speed of light? That will contradict the statement that speed of light is always constant. So, my law of addition of velocity must change in such a fashion that this does not happen, and it does. But I am not discussing special relativity fully, but yeah, you are right. Okay, so let me make one statement because I can take 5-10 minutes, no? So, and the statement is the following. All right, this is fine generalization. We made one jump somewhere and gotten into this funny thing of minus c square d square. Is this any real thing? Do the clocks really go at slow speed? Or is just some mathematical stuff you have done? How do we test it? So, this change in clock rates is called time dilation because of the formula that this expression being what it is. Okay. And the answer to that is yes, it is experimentally seen. And how do you see it experimentally? Well, the experimental thing is the following. I will be very brief about it, but just indicate what it is because I am running out of time. It so happens that the cosmic rays which hit the upper atmosphere, they are mostly protons and they produce pions interacting with the nuclei of the molecules up there. They produce pions, pions will finally go into decay into mu mesons or muons. Okay. And these muons further decay into electrons and neutrinos. So, this is the process, physical process that happens. Now, it so happens that, so you have the process P plus nuclei goes to pions, which goes to muons, which goes to electrons plus neutrinos. This is the process, elementary process which takes place. It is this process which has the property that on an average muon will decay, that means muon will get converted to electron or whatever it is in about 2.2 microseconds. This is something that you do experiments in lab and see. Okay? There are a few subtleties here, but let me gloss over those. Okay? So, this number is 2.0 microseconds. It is called the average lifetime of a muon at rest. That is in the rest, whatever is, that is what you see in the lab. Okay? Now, here is my atmosphere. Here is the muon counters. I find out how many muons are passing through per second at this level. I find out how many muons reach here. Now, remember, muons last only for on an average 2.2 microsecond. If they are going at speeds which are, remember also in that formula, if V is very close to 0, much smaller than c square, then that is same as that there is hardly any change in clock rate, which is why you do not see the time differences, we just go in a car. Okay? But if that V is very close to speed of light, then that change is significant. Now ask the question, if this is going, if muon is coming down here with some speed V. So, as an example, let muon be traveling at v is equal to 0.98 speed of light in actual experiment which was done by Hall and Rossi in 1940. The values that turned out to be about that much. Okay. If that is the case, then it will take certain amount, and let us say this height is let us call it say 9 kilometers. In the real experiment it was only 2 kilometers, but here for illustration purpose I am taking these numbers. So, this is the muon is going to travel from here to there, the distance is about 9 kilometers. So, if it were to travel at speed of light, how long will it take? So, 9,000 meters. I need some space now. Minus 5 seconds, right? Approximately. Is that right? I may make mistakes, please correct. Okay? Now, this is larger than this microseconds. Which means if I start with certain number of muons, some of them will decay, and roughly let us say this lifetime is related to half life with some factor. Let us not worry about that factor, let me pretend this to be the half life just for sake of argument. So, the calculation is easy. So, how many half lives will be there here? So, this is about 30 microseconds, this is about 15 lives are there, right, which means the numbers will deplete by the factor of 2 power 15. So if there are 2 power 15 muons per second here, roughly there will be 1 muon coming down, right? That is what one will expect. However, if this 2.2 microsecond statement is a statement of muon decay when muon is not moving, I mean roughly close to 0 speed, okay, then that is the statement, but it is moving now. Now muon decay to half rate can be thought of as a clock, or you can imagine an observer or person measuring there is falling with muon. That fellow has a clock. That fellow is moving because muon is moving, but moving clocks have a different tick rate. By how much does it change? By the formula that we have upstairs. So then, so this implies about 15 half lives, roughly, right? 30 divided by 2.2, whatever, some number, okay. So that means the depletion will be that much. However, this 2.2 microsecond is not the right thing to do, because that clock rate, because I am measuring this 9 kilometer distance is done by my clock. So I am the clock at rest. My map is the earth map, okay. That is my time which I am looking at, that is the time it takes. This is my clock. Muon clock is different because muon is moving. So what is the factor that you will get? That 1 minus v square by c square factor, it will enhance by that. So half life of moving muon will be 2.2 divided by square root of 1 minus v square by c square, and this number is I think this is about 2.2 into roughly about 5. I calculated it. You can check it. I have done the calculation, so I don't want to write. So this factor is about 1/5. So that this number will become 5 times more. That means this will be approximately 10. Okay, this is delta t, the time. So I will, although muon when it's at rest is decaying at 2 point, with respect to my time, if I can know what is half life is, that should be about 10 microseconds. This is only 30, so only 3 lives will be gone. That means it will deplete only by a factor of 10, 2 power 3. So instead of 2 power 15 is depleted by a factor of 2 power 3. So ask the question, given the rate here, what is the rate of muons observed here? And from that infer what should be the speed of light, I mean the speed of the muons, what should be the v. It turns out experimentally that this v turns out to be the number that I quoted, and what you see here is not the depletion that you expect from 15, but depletion that you expect from 3, which means the clock which is moving as defined by the muon half life is actually taking at different rates compared to our clock. Okay. So this is the proof of time dilation effect. So that effect is not simply mathematically that we arrived at, though it can be arrived at the way I described, but it's a physical effect which is there. Okay. Now I will just make 2 comments. One is that the same kind of map, you can now generalize the map from that simple expression to a different expression, and that will tell you that the clock now introduce gravity, so make that metric which is different, that a clock which is at height will take at a faster rate compared to clock which is at sea level. This is called a gravitational time dilation. I will not discuss it, but can be derived exactly same manner, the metric will change. Okay. Now these 2 effects, that the clock's rates are affected because they are moving and clock rates are affected because they are in gravitational field, both effects are essential because they will affect the travel time of signals from the satellites to your GPS device. And if they affect that, if you do not take into account that, your GPS calculation will be completely haywire. Experimentally, when they first flew the GPS satellites in 77, it was pointed out you must take into account this and just correct for this error. If you do not include that, they said no, we do not believe this is too small, 1 part in 10 power 10, it does not matter. So they put the instrument, I mean put a device which can make the correction to the clock, and then the clock was flown, and in 3 weeks it went out of synchronization. So proved that gravitational time dilation has to be taken into account. Only when you do it, you will get the GPS distance, we will say within 10 meters or 15 meters. There are many sources of errors, etc., etc. But all these effects which are coming from the simple, relatively simple, there are conceptual jumps here, of course, simple calculational methods by which actually affect the practical matter. So we began by saying that practical problems introduce the abstract notions like metric here. Same notion then give consequences which are validated by experiments, and they also feed into the actual technology, the real practical thing like GPS that you use in the mobile, it actually impacts there. So that's the chain of logic I wanted to follow, which is what I have done. If you have more questions, you can ask me later. Tomorrow I will talk about completely different topic, not this one. So thank you.